Hello, hello. Hey, Thomas.
Hey, Luca, what's up? What was
Yeah,
new at PyTorch conference? You were there, right?
yeah. I was there. I was there. Bummed that you couldn't be there, but yeah, it was a lot of fun. I was there with Sebastian Rashka, um, and it was pretty fun to see the uh, people passing by. I said, "Sebastian is there," and let me shake the hand. So it's good. It was it was a lot of fun, and he's super humble. So yeah, everybody got to know him and so on. And then we had a keynote on the Lightning stack in general, and a talk on Thunder. So it was a breakout session. The room was pretty full, and several people came after to talk about Thunder. There's a lot of interest from different sorts of people. Some of them are people needing to modify computations because they need to run on certain devices or they need to optimize it and say, "Oh wow, this looks pretty good to do that." And I actually used one of the example that we're that we've been working with in the last three episodes to describe the fusion, right? The manual fusion, and that kind of clicked uh, with people. So that's great. That was great. Um, and then what else? Well, Llama 3.2 got released. I have nothing to do with that, but it's a
Yeah,
but it's a good target for us, right?
yeah. I mean, the nice thing is that with Thunder, you can as long as they don't have like completely new operations. If you had an optimization for one thing, you just drop the different model into ThunderJIT, and out comes the optimized thing, right?
Yeah, yeah, absolutely. Plus, we've been thinking about some more like friendly way to package up transformations and so on and so on and so forth. So we'll be able to kind of deliver with Thunder the package that works for that model, that family of models, and have it. If you don't want to exactly know how to use the lower level API, you can still apply things and they just work. Okay, so last week, so going back three episodes, we started with a simple model. We replaced the kernel with Triton with a Triton kernel. It was the matmul, and then the next episode we fused the matmul and the ReLU manually, and then the last episode we implemented backward for it, so that we now could run backward, forward and backward, and do optimization and training. And then we've been mentioning this Liger thing that for people that haven't followed, it might be kind of an acronym. What is it? Well, Liger is an animal that is the inbreeding of what is it? A lion and a
Lion,
tiger. Yeah,
like,
yeah.
right?
It looks a bit weird, but I'm sure it's a fun animal to be around. But it's actually a set of kernels that a team at LinkedIn hand wrote in Triton, and that they kind of modeled after the Hugging Face implementation of transformers. So you can just monkey patch with the ops, and so you can replace certain kernels and introduce fusions. And there's a bunch of them. Like, let me share my screen maybe, and I can just show what Liger is about because it's a very cool project, and kind of got in touch with the authors and super nice team. We're very happy to have their
Yeah.
collaboration. And so essentially, this is the Liger kernel repository, and it has, yeah, kernels. And if you go in here, you see ops, and each op is, for example, Swiglu. Guess what? It's an activation function that has been kind of fused together, and there's a forward, a backward, and these are the ops. But if you want to look at the kernels, this is the Triton kernel, right? Um, And then there are a bunch of others. There's RMS norm, rope. We'll talk about rope a little bit. So now that Llama 3.2 has been released, our idea is like, let's apply the Liger kernels to Llama 3.2, but let's not do it on what has been what the kernels themselves and the ops have been modeled on top of, right? Because they basically say, okay, if you have a Hugging Face model, then where is it here? You can apply the kernels directly here, you see. So they are basically patching the Hugging Face implementation. So these kernels and the ops are basically replacements for Hugging Face implementations of the same in the same kernels or a fusion of kernels and so on. So they go in, they patch it up, and so on. What we've been talking about all the time here with Thunder is that if you have any model, any implementation, you put the code in a canonical form by tracing it, and then you can transform it and apply whatever optimized kernel. And so we'll try to do exactly that. On top of what? On top of LitGPT. And again, let me share my screen so I can share the repo. So now we provide a bit of guidance because sometimes we kind of jump over and
you can see like the last commit is very recent.
Oh yeah.
And that is the Llama 3.2 one, right?
Yes, it's 1 hour ago. Sebastian, that we were talking about before, merged the Llama 3.2 support for LitGPT. And LitGPT is a minimal implementation of a lot of language models, and minimal because the language models that are implemented, there are over 20 of them, are basically contained in this file. You know, it's like 500 lines long, and it's all in there. So it's not that one implementation is 500 line long. It's all of them because they are all very similar to each other. And so this now supports Llama 3.2 as well. But the way things are laid out, like for example, the way we store KV, KQMV, it's a bit different from Hugging Face transformers. So now the exercise is, can we use Thunder to acquire whatever LitGPT does and then apply the Liger kernels on top of it just as a transformation? And so that will be the adventure for today.
That would be fun.
Yes. So we saw a lot of ops there. So which ones do we start with? Like ops of, we have the activation function, the rope, the whatever.
Yeah, so we start with Swiglu. You mentioned it before.
Yeah. Okay, great. So let's start with Swiglu. If you want to share your screen, that would be great.
Yeah, so let me, and I put up a studio with all the examples. If you go to Lightning AI and you search for Thunder, you find the Thunder tutorial, but you also find the studio with the all the notebooks that we had so far, and so you can use that to check out and see what we've been up to. Okay, can you see?
Yeah, it's called the Thunder Sessions Studio, Thunder Session Demos, actually. So right. If you go to lightning.ai/studios and look for Thunder, that one will come up.
Let me.
Yeah, here's a collection of
the education. I think
it's fine. If you go to templates, you will still be able to get the public one.
And then search here for Thunder. And it will be, we have the 0 to Thunder, which is the basic tutorial for Thunder. And there's the Thunder session demos, where you find all the Thunder session notebooks, except the one that we're going to write today, right?
Yeah, because it's live. Yes.
Okay. But great. So I pre-installed like the latest version of LitGPT and also downloaded a few checkpoints of Llama 3.2, as well as I installed Liger. So
but you're in Europe. How did you do that?
Well, so it's only the combined vision models that
okay, yeah.
right? I mean,
But
and
technically, yeah,
also obviously all the derivatives, they don't like, I mean, I wondered like how Meta did it. I mean, they needed to approach probably Hugging Face to implement this limitation on the Hugging
yeah,
Face hub, right? Because uh, uh, they needed
yeah,
it.
for sure.
All the derivatives will probably not use it. So, oh well. I think it's more to make a point than it is
Sure,
straightforward.
sure. Also because Olama was officially supported and Olama didn't have this limitation. And also, if you go to Lightning Studios, kind of doesn't run in Europe, right? If you don't want to. So the
Right.
managed cloud doesn't have this limitation. So you can still download it there. You just watch it from here, but the files are there. So kind of works anyway.
So, Liga kernel ops swiglu is the module. And now if we look what's inside the module, we
Mm-hmm.
see there's a number of things like functions that sound very detailed. And then there's swiglu forward and swiglu backward, and those will be the things that we will be using. There also is a Liger silo mol function, and we'll see a bit what that is about, right? So
Yep.
let's look at the swiglu forward, and yeah, so it's simple enough. It just takes A and B, and what it does first the silo nonlinearity, and then it multiplies the second operator to it. And we can also start importing libgpt, and we want, of course, to import Thunder, and we want to import Torch because otherwise it's half the fun, right? Okay, so you see that it is like very fresh everything, and it has migrated my cache now. And so if we take, for example, now here a little demo model, so with torch dot device CUDA, and I'm on this L40S GPU here. But let me just take a very small Llama model. But so this could be libgpt model, and then GPT, and we can instantiate it from name. And now we need to know the name for the llama. So let's see if I can get it right. Llama 3.21 billion. I think that's it, right?
The org, I think, is like llama slash, no? The prefix.
Do I need this here? No, it works like.
No, because you have already have the checkpoints here, right?
Yeah, so it's not the name that I need to download the checkpoint with the MetaLlama prefix, but just for the model structure, it's like this.
Okay, okay. Yeah, right.
And so the other thing we will of course need is some inputs, and so I will be lazy and I will just use a dummy input, let's say a range 16. And this will be our input for a toy thing, but we want the batch dimension, right? Okay, and so let's look at what M is. Well, it looks like a llama with 16 blocks here. So this didn't change too much. Yeah, and if we like go into it enough, we see that, oh, we can JIT compile it, right? So JM is Thunder JIT of the model, and then we can run it with our inputs. and see if this works. The first invocation after jitting always takes a while, and then we can look at the last trace and of JM, and we will see what that gives us. Yeah, so I think this takes a minute approximately.
Yep.
And so going back, let's recap. So Swiglu, we will need to define, in order to define a custom operator, we need an implementation. That is easy. It will be like calling this function from Liger kernel, but we also need the meta, right? And so maybe we just start writing that. So, last traces. So this is a pretty long thing.
Yep. Will we see the Swiglu in there?
Yeah, I think we will kind of see it. So
Yeah, let's maybe take a look if we can spot it.
if we search for Swiglu and search in the cell outputs, yeah, we have it somewhere in the cell outputs, but it might be, no, we're not seeing it. And but if we look at the silo, which was mentioned in there, I think we should see that, right? But we don't see it here. We need to go back.
Oh yeah, because it's the last trace, right?
Yeah,
we
because
should probably
it
look
has
at
all
0.
been
Yeah,
used by NVFuser, right?
exactly.
If we look now, we see that here actually is the
Oh, there it
signal
is.
in two parts. And so the first is calling ltorch silo, and then we have the multiplication here with the second input. And so this will be, and here you see the line, the source code line, right, from the legibity that does exactly that. So this line with the silo and the multiplication here is exactly what also the Swiglu does. So let's define.
The whole point will be, say, like the whole point for Liger in this case is, instead of computing Silu, which is one kernel from PyTorch Ligger, times something else, just use the two things. Probably NVFuser or Torch Compile will do it, right?
Right.
But we're going through doing this manually because it really where we want to get to.
Right. And so the first thing is we need an executor. So Liger executor will be Thunder extend operator executor. And I think we need to provide a version, let's say 0.1. And so we can start right away writing a meta function. So like any activation function, we can, not Liger, Swiglu, forward, meta. And so we had A and B, and so this is simple. So this just returns, because it is in the end a pointwise function, it returns a tensor proxy, and it needs to be a Thunder tensor proxy. That is like A. So it has the same shape, the same D-type, and all that. Okay, and with that, we can define our first operator. And so this will be Liger. And I'm trying to stick to kind of the scheme that I name it meta, and then forward will be the operation. And we register this as an operator with the Liger executor, and we give it a name, Liger Swiglu forward. And the meta function we just defined.
Perfect.
So
basically, the executor will contain more and more operators as we are adding them.
Right. And so the function that does the thing is just this one, right?
Yep.
Okay, so that was easy enough. But now, do we want to do the backward first, or do we want to do the fusion first? Because we don't have.
Yeah, let's exactly, because we don't see anything in the trace, right? That says this is Swiglu, right? Because we just look for it. We have a Silu plus the multiplication. And so if we wanted to do it without Thunder, we would have to either have a function that we can monkey patch, or if we didn't have a function that defined Swiglu as a call, it would be pretty tricky to replace, right? Because how do you replace just two operations out of like a sequence, right? So we would have to go back and change the code. Nothing happens if you change the source code, but sometimes you don't own the model. And so that's also where it comes from. All right, so what we need to do is to go into the trace, grab these two operations one after the other. This is reminiscent of what we've done with Matmul and Relu just a couple of episodes ago, and then replace it with our new operation.
Right. And so should we type it out again, or should we try to copy paste from last time?
I mean, you can copy paste away since it's we've already done it. It's your call if you prefer to type it out, but it's always on the
Well, I don't know. It doesn't
up to
matter
you.
much to me. What keeps you entertained better?
Well, I have a sadistic approach to things. Having you type is more fun, but no, you can just copy paste. So we are moving faster.
Let's copy this one, and I'll type out the next one. How about
that? Yeah. Sounds good.
And so let me copy this here. And now what do we have? We did get the consumers and producers from the trace in order to be able to see, like, when we hit the first thing, like the silo, we need to check if the consumer is actually the multiplication. And then we started a new compute trace in order to have the transformed trace somewhere. And then we iterated over the bound symbols. And a bound symbol, remember that this is like a function call. A symbol is like a function. A bound symbol is like a function call in the trace. And
with the arguments attached to it, right? The function call with the arguments, yeah.
Right. And after we have fused it, we will want to skip the multiplication. And so this stays in there. And so the symbol we're looking for now is Thunder Torch Silu.
Yep.
And we don't need to worry about any bias arguments. And we grab the consumers. So if we needed the output for the silo for more than one thing, we can fuse it because we need the output. And the whole purpose of fusing is avoiding creating this output. And the other thing needs to be a multiplication here, right?
Yep.
And so we can have the multiplication as the only consumer. And now we want to be a bit flexible because you could have like the multiplication commutes, and if for whatever reason somebody spelled it out the wrong way, we would want to be lenient. So we have the left factor and we have the right factor, and this should be the args of the multiplication. And so if the left factor is the output of the silo function, then the other is the right one. And if not, we hope that the other is the left function, right? Because there's no more, and because it was a consumer, we know it has to be one of the arguments. And so then we can replace the silo symbol with our Liger. I need to stop.
I don't know. Maybe it's legal.
Pronunciation, right?
Yeah.
And the output should be the output of the multiplication, and we don't want any subsymbols. But we also need to construct a new set of args because we have different inputs now. And so the arguments would be the input to the silo function, and yeah, we should check that it's the only input, but let's not be too holy here.
Yeah.
And then we need the other factor, and this should be the arg to the fused thing. And then we add the multiplication to the symbol that we don't need anymore.
And we don't need bind process anymore.
Oh yeah, this I fixed because I don't like typing it out. And and this has been constructed by fuse Swiglu transform with some capitalization pattern there. I don't know, do you capitalize the G or not?
Yeah, because it's gated linear unit. And so it's swish gated linear unit. So the SWI is one word with the S capital S and then GLU.
Obviously, there's a whole science in naming these things. And that's our transform. But do we want the backward immediately, or should we first try on the transform?
I would try it out and see if it works.
If you want to try it out, we see that it won't work unless we disable the gradients. But obviously we can do this. So we do, let me make this smaller. No? How do I get this? Oh, let's comment it out so it doesn't get in the way. So we can now define our JIT model as Thunder JIT, and we need the model, and then we have as executors our Liger executor, and as transforms, we want the fuse Swiglu transform, and with torch no-grad, because we don't have the backward defined, or otherwise it will say, yeah, I need a backward, I don't have one, I can use this. And so we need to do this, but now we can do the result as jmint, and it will take a minute to run here because it needs to reacquire the program. And maybe we should have just taken one layer, right, in order to save time on the video.
No, it's real life. If you have a 1 billion parameter model, it's going to take a minute to acquire. Not that like raw acquisition speed is something that we have explicitly optimized for a long time in Thunder. So there may be low-hanging fruit. You remember our interpreter.py, but it's not slow per se. It's just that it takes time.
Oh, it still says not implemented, even though we have no grad. That is bad. But so I could
then I have an idea. Why don't we define grad? And then we'll fix
yeah,
this during
you
the
have
week.
the best ideas. So let's go up here, define the grad here. So we first need the backward. So and the pattern is much of the same, right? We have the let's look at Tiger kernel ops swigglue and swigglue backward. And so this takes A, B, the two inputs, and the gradient for the output. So the Liger swigglue for backward meta will take A, B, grad out, and it will return the gradient for A and B, and those are tensor proxy. Like we could use A, B, or grad out. They will all have the same.
It's Thunder tensor proxy, right?
Oh yeah. Okay, that was easy enough. But now we also need to get the operator. So Thunder swigglue backward is the operator, and it has the name again, and the meta function is our meta function, and the implementation is Liger kernel ops swigglue. And for some reason it doesn't give me good autocompletion here. Okay, and so this is the backward, and now we need to hook it up, and this was with a grad transform, right? Liger swigglue grad transform, and this needs to take the same parameters as the forward, and so we first call the forward. So the result is Liger swigglue forward. And Thunder, when it constructs the trace, it will execute this and with the meta functions, and then it will like take it apart, right? We had this mechanism where you said grad res is Thunder transforms. Now Thunder core transforms get grad of res, and then we can call the backward because we now have A, B, and grad res. So the grad A and grad B will be Liger swigglue backward of A, B, and grad of the result. And we need to put the gradients Thunder core transforms.
Yeah, we need to make this more accessible, right? So that you don't need to dig into Thunder core transforms.
One thing we need to figure out is like where to put these functions. I think that will help a great deal. And so the gradients for A and B will be grad A and grad B. And the other thing we need to improve is we need to improve the error message when we forget to return the result, because it will just say some name was not found, and it will be a random name. But things to be improved.
But this is nice because it's really close to what you would write in your notes. So it's really understandable. I like this API a lot.
Yeah.
All right.
So now we register an implementation. And so this is the implementation for Liger Swiglu forward. When it sees this, if it doesn't need to have gradients, it can just run the forward. So this will be the execution transform. And the word transform is used in a very loose sense. But the gradient transformation, the grad transform will be a little bit more interesting, right? And so that's it. And now we can do the same thing again. And we can...
Yeah, probably the name transform there could be improved because like if by transform we intend something that we implement and pass as like trace transformation, this is a bit higher in level of abstraction. So maybe we can, we can give it a better name there in that API.
Well, yeah, so we have overloaded the name transform here a bit.
Exactly. Yeah, that was what I meant. So probably you can, but you know, it comes from a time where transforms were not so well like defined in Thunder. So the fun it's not that we sat down and designed Thunder the way it is now. It kind of evolved over time, and so we're consolidating things. And so yeah, it's a very nice time because it's like a Tetris, right? Everything is falling into place, and you get a nice like thick thing.
Oh no!
As thick as this error message. What is this?
Okay, like a Swiglu forward apparently returns a tuple instead of
Okay.
just a
You
thing.
need to look at Liger itself.
But I think I know what's going on. So what I showed you was, and of course, the Liger kernel people, when we ask them, say, can you like add forward and backward for all the ops, they were very responsive, and I truly appreciate that. But so I think the Swiglu forward, because you need A and B for the backward, the forward returns A and B actually. And so
yeah, exactly. It returns A and B and then a view on C. Yeah, I'm checking their implementation.
Yeah, so we need to. One way could be that we return this, but maybe the cleaner way is to do this. We take AB,
yeah,
and then we just call the function, and the result, of course.
yeah.
And so we call this with A and B, and then we return the result, all that we need. And here the implementation will now be this implementation function. All good.
Awesome.
I think in the initial version, I programmed that a bit differently and tried to get by. I mean, I could have adapted the meta to be different and all this, but I think it's more fun.
I think this is a good example of a pattern you will want to do, because if you're returning A and B, then those A and B won't be used probably, and they will be just removed.
Yeah, so right. It's a bit tricky what what to do there, but yeah.
Yeah. So anyway,
yeah,
as you can see, there like devil is in the details, but I believe that the formulation that we have today allows you to reason through all these things because they are in front of you, right? So instead of being deep down somewhere in the framework and what's going on, I don't know. All right, so
yeah, so we could now use torch testing, assert close. And of course, if I run it again, it will be fast, right? So I can rerun it, and I can assert that like res is close to the reference, and it works. So amazing. But
Yes.
Liger people are very serious about testing their kernels. It's a rigor to really take a slice from and learn a great deal. But we can also check that we fused. I mean, we know that it fused well because we got the error message, but we can also like
let's take a look.
Insert any one of the bound symbols, at least one should be in the Thunder last traces of our JIT module, and the last one of these, I forgot the in, right? And so one of them at least should be the Liger Swiglu forward. And I forgot to say I want to iterate over the bound symbols. And so this is great, and we can do this for the backward trace. Let me, and then it would be backward, and this will be in the Thunder last traces, last backward traces. And of course, we can also check, like, should we check a gradient?
Sure, let's go for it. And then we can also time it, and maybe we won't see any difference. So it's all good, but just for the sake of it, because we'll be building, right? Right now, our mission in the next episode or two is to add more Liger kernels to the LGPT implementation of Llama 3.2 and see the effect that it has in the different sizes. So that would be pretty interesting to follow.
Yeah, so we need actually a grad output. So this is just torch random like the output. And so then we can use torch autograd grad, and so we want to differentiate res, and let's just pick something. So jm get parameter, and we could use, for example, transformer wt weight ring as a parameter.
You didn't want to differentiate Go? No?
Oh, and the gradient out is the start because it's not a scalar variable.
Of course.
And I could use the sum, but this is kind of my level of rigor. It's not to do it too much, but do it a bit. And so we can compare these. Let's see if we get them. Attempting to Kublas, but there was no current context. Oh, this is a terrible error message. But did it work nonetheless, or? Yeah, it's just a warning, so we might be able to ignore it. And we could try torch testing assert close and grad res and grad ref. Oh no, they're not close. But so the greatest relative difference is 1e minus 5. So we do rtol, well, 2e minus 5.
This is p hacking. But like, of course, we need to expect that like gradients are a bit more sensitive.
Usually you would do this, you would do gradient tests with 64-bit floats. And
exactly.
And remember, this is like it's not like a single operation, but we did this through the entire
1 billion.
Llama 1 billion. So it's
Exactly.
pretty neat. But of course, the Liger people, they took it a step further because they were unhappy. And so they actually, I think they do convergence tests whenever they change a kernel. So, yeah.
Anyway, that was amazing. Like, yes, this is a start of a 1 or 2 episodes where we'll hammer in all the operators and we'll show how to go end to end on things. And then we'll be able to compare, like, how does NVFuser do it? How Torch Compile does it? How Liger does it? Oh, yeah. We're over time by a lot, but I think it was super interesting. So let's do it.
Okay, so Res, do you want forward, backward, or just the forward?
Yeah, let's do forward for now.
Okay, so let's do Torch CUDA synchronize.
Yeah, don't forget.
Compare.
If you're doing at home, synchronize your CUDA.
Yeah. Oh, it's int, not imp. Okay, so now it doesn't compile again, happily. So it should be faster, but it runs it a number of times in order to get it. And so it's 16 milliseconds when we run it with Thunder and with the Liger kernel. And it's 13 without. And that's probably not the fault of the Liger kernel, but it is of the Thunder bits. If you want speed with Thunder, one thing to not forget is to also have the get default executors here. And so this will include NVFuser, hopefully. But now it's slow again. No matter.
Yeah, but let's do it, no problem. Yeah, because what happens in fact is that we didn't even have without any other executors. Were we wait, I don't recall right now. So were we decomposing and running the prims? Or
yeah. So one thing is we decompose and then run all the decomposed things with PyTorch directly, whereas usually you would the things that are decomposed would then be fused by NVFuser. And so
yeah, but I wanted to explain to clarify, because why is it slower than eager, right? Because when you have like Silu, for example, and we saw Silu, right, in the trace, but then we saw all the comments below Silu where we said we had prim this, prim that, and so on. So when you don't have executors, like for example, you could have a PyTorch eager executor that will take the Silu directly. If you don't specify anything, the fallback is to decompose the operations. And when you decompose those, then you're running the decomposed one. So instead of fusing, you're actually breaking things up even more. But that's the fused, like the decomposed ones, are the ones that fusers like NVFuser like, right? They like it a lot because with the smaller amount of primitives, they know how to put it together into custom, like just-in-time created CUDA kernels. And now when we put the fusers in the mix as the executors, now we're much faster than eager, and we're using the Liger kernel. So, but the Liger kernel will only fuse that one bit, and the rest of the operations will be fused by NVFuser or whatever other executor that we put there.
Dispatch the attention will be dispatched and all these things, right?
Yeah, exactly. So then we end up being much faster. Awesome. That was great. Amazing. Thank you, Thomas.
Yeah, thanks, Luca.
Yeah, see you next week.
Yeah.
Have fun.
And more Liger next week. And
absolutely. Exactly. Llama 3.2, Liger, faster and faster. Bye-bye.
See you.